Good morning. So today we're going to talk about independence. This is section 6.5 in your textbook. And so independence is a concept of whether or not the one event affects the outcome of the other event. And so independence is something we're interested in because it allows us to do several other things if we know that that has occurred. So for example, let's say we're going to roll 2 fair dice, and I want to know what's the probability that the first die is a 6. The first die is a 6. So I know that I have 36 outcomes for my 2 dice here. First die being a 6, there's 1, 2, 3, 4, 5, 6 of those. And so I get a probability of 6 out of 36. I put that into my calculator. That's going to be 1/6, which is 0.16 repeating. All right, so I can round that to 3 decimal places here. Remember, always use at least 3, if not more. It's going to be about 0.167. Wow, my handwriting is terrible. Just excuse that, okay? All right, now, if you roll doubles, what's the probability that the first die is a 6? Or in other words, the probability the first die is a 6, given that I know I rolled doubles. All right, so in this case, given that you know you rolled doubles, we have a reduced sample space. Okay, so that conditional probability means that I'm only looking at the doubles, which means that my denominator here is 6 now instead of 36. And 6 instead of 36, and out of those 6 that are doubles, there's only 1 where the first die is a 6. That's 1 out of 6, and that's going to give me 0.167. Now, as you notice here, it doesn't matter if the first die is a 6, the probability hasn't changed, and it didn't matter if we got doubles. So the fact that getting doubles and knowing that you're only looking at doubles does not change the probability of the first die being a 6. So because these two probabilities are the same, what we would do is we would say getting the first die to be a 6 and rolling doubles, these are independent. And the argument for that, for independence, looks like the probability of something happening is the same as the probability of that thing happening given that the other thing has happened. Okay, so in other words, the conditional probability is the same as the original probability. And since those two things haven't changed, it means B didn't really make a difference. It didn't make a difference that I got doubles. I still got the same probability for the first die being a 6. One did not affect the other, and so therefore those two events are independent. All right, now the next question down says, what is the probability of getting a sum less than 5? A sum less than 5. All right, so less than 5 would be, let me change colors here real quick. Okay, maybe. Thanks for your patience. Boop. All right, so a sum less than 5, we're talking about, oh, I just moved all my dice. Yes, this is talent, folks. All right, so I've got 1, that'd be 3, there's 4, but we want less than 5, so there's 5. I'm looking for, it looks like there's 1, 2, 3, 4, 5, 6 values that are less than 5. So again, 6 out of the 36, which gives me 1/6, which is 0.167. Okay, so it says, what is the probability? So if you roll doubles, what's the probability that the sum is less than 5? Okay, so if I roll doubles, again, I'm only looking at the 6 that are doubles. And out of the 6 that are doubles, it looks like 2 and 4, those would be sums less than 5. That's 2 out of 6, and that is 0.3 repeating if we were to turn that into a decimal. Okay, so in this case, getting doubles did change the probability. In that case, so we would say that getting a sum less than 5 in doubles, that these are not independent. So in other words, you can say they are dependent, but these are not independent. And what's happening here is that the probability of the event happening is not the same if you have some sort of condition applied to it. So since getting doubles did change the probability of getting a sum less than 5, those two events are not independent. Getting doubles affects that probability of getting a sum less than 5. All right, so events A and B are independent if and only if knowing whether event A has occurred or will occur does not change the probability that event B will occur. Okay, so knowing that your event happens doesn't change the probability of the other thing. So notice that my probability of A is equal to the probability of A given B. Okay, so the probability that we're looking for, that A or that B, whichever one, should not be changed by that condition if we have independence. Okay, we also know, okay, so basically what we're looking for here is if these two things are independent, we would expect to see the probability of A equals the probability of A given B. if I want to make this argument, I would say if these two things are independent, the probability of A should equal the probability of A given B. In other words, B shouldn't change this probability. Then I would actually find the probability of A and the probability of B and see if they're the same. Okay? If they are the same, I would conclude and I'd say, so therefore they're independent. And if they're not the same, I'd say, but they're not the same, so therefore they're not independent. So that's that argument that I would expect to see. Again, this is what I expect to see, this is what I actually see, and so what? What does that mean? Now, another thing that can help us with independence is that we know that if the probability of A is equal to the probability of A given B, okay, we know that we can use the multiplication rule. We learned in our last section that A times B given A, that's A times B, but you know A has already happened. So if that doesn't affect, if they're independent, then the probability of B would be the same as the probability of B given A, if the two events are independent. So if you know that the two events are independent, you can actually do A times B to find that missing intersection value, that missing AND value, as long as you know they're independent. Now you have to be really careful about that. You can't assume, okay, that the conditional probability is equal to the other one. But if you know they're independent, then you know you can multiply the two probabilities together to get that intersection. And it's because of what I've got highlighted here, that if they're independent, the probability of B given A and the probability of B would be the same. Okay, so you want to add this to your pile of things like mutually exclusive, when I see independence, I know two things. I know that A is equal to A given B, and I also know that A times B would give me that AND overlap. Okay? All right, now a couple other things that just sort of float up about independence here. We know that if two things are disjoint, then the probability of A and B is 0. And we just said that if they're independent, then the probability of A and B is probability of A times the probability of B. So if you were to put those together, if both of those are equal to the AND, if you set them equal to each other, then what you're saying here is that if two things are disjoint and independent, then their product has to equal 0. The only way that could happen is if A is equal to 0 or B is equal to 0, meaning one of the events is impossible. Okay, so most of the time, unless you have an event that cannot occur, they can't be disjoint and independent. It's usually one or the other or neither. Okay, all right. So how can we use this independence idea? So I've got this a couple of arguments over here. I've got a table, and most of this work is already done here. So are the events prefers dogs and female independent? Okay, so I would start this argument. I've got these two events, prefers dogs and female independent. So I would start, if they're independent, then I would expect the probability that someone prefers dogs to equal the probability that someone prefers dogs, given that they're female. In other words, knowing that they're female shouldn't change that probability. Okay, so I would go up to my table and I needed to find the totals, and I would figure out what that is. Well, the probability that someone prefers dogs is 58 out of 100. Okay, which is 0.58. Okay, and then the probability that someone prefers dogs, given that I know they're female. So given that I know they're female means I'm only looking at the 54 females. And out of the 54 females, I know that 22 prefer dogs. Okay, so out of just that column, and I do my calculator, I go 22 divided by 54, and I end up with 0.407. All right, so my argument is if they're independent, then the probability that someone loves dogs, it would be same as the probability that someone loves dogs given that they're female. Like the female shouldn't change that. But they do not equal. Those are not equal. So I would say so. They are not independent. Okay, what do I expect to see? I expect to see the probability and the conditional probability would equal the same thing. They do not equal the same thing. In fact, here's what they equal. So therefore, these are not independent. Now, if I said, are the events prefers dogs and female disjoint? That argument would look like, well, if they're disjoint, then the probability that someone loves dogs and the probability that they're female should equal 0. So that's what the definition of disjoint. So what do I actually see? Well, the probability of dogs and someone being female, that is 22. Remember, this is just an intersection, so it's not conditional. 22 out of the 100. And then I would very specifically say that that is not equal to 0. Okay, so 22 out of 100, which is not equal to 0. Okay, so also these two events are not disjoint. So this is our mathematical, our statistical argument for both of these. Here's what I expect to see. If they're independent, I expect this. If they're disjoint, I expect to see this. Here's what I actually see. Here's what that probability actually is. And then so what? What does that mean? Okay. All right. Another way that this shows up is, so for example, let's say that the probability of A is 0.54 and the probability of B is 0.2. And then it says if A and B are independent, what is the probability of A and B? So if they are independent, what we know is that the probability of A times the probability of B should multiply together to give me that cross. Okay, so in order to find this, I should be able to do 0.54 times 0.20. Now I can only do this if they are independent. If it doesn't say that they're independent, I would have to say I can't find this number because I don't know what the conditional probability would be that matches up with it. Okay, and that gives me 0.108. 0.108. All right, you are typically on time to class 90% of the time. Assuming that travel between classes is independent, what is the probability you are on time to your next 5 classes? So again, independence tells me I should be just able to multiply. That means the probability is going to stay the same every single time. So 0.9 times 0.9 times 0.9, 5 times, and that's going to be 0.590. So one of those repeated events ideas. Okay, all right. So here's going to be, looks like I'm seeing percentages of percentages. Let's see, again, this is that same problem that we've been working. So you survey people coming out of a movie theater, you note their age and whether or not they enjoyed the movie. 35% of people were under age 13. So I'm going to say under age 13, that is 35%. 40% were between 13 and 50. And the rest were over age 50. Okay, the rest. All right, so I've got 100% minus 0.35 minus 0.40. The rest should be 0.25. Okay, there's the rest of my 100%. Okay, and again, this is kind of just practice. Of the under 13-year-olds, 90% said they enjoyed the movie. I'm going to use a little heart for enjoyed. 90% said they enjoyed. Which would mean 10% did not. Okay, use a little frowny face there. Of the under 13 years, while only 50% of the 13 to 50s enjoyed it, which would mean that 50% did not. And only 70% of the over 50s enjoyed it, which means that 30% did not. Okay, and it says draw a tree diagram of the results and calculate the probability of each outcome. All right, now in this case, these are not independent because the 90%, the 50%, the 70%, those are conditional based on the ones before. So instead of using the idea that the probability of A and B here, when we want to find the fact both of them and where they cross, okay, in this case, we're not going to be able to say probability of A times the probability of B. Instead, we've got the probability of B given A. So each of these secondary branches, those are not independent probabilities. Those are conditional probabilities. It's 90% of the under 13-year-olds. So when we're talking about the difference between the previous example and this one, knowing that you were on time to class the first time doesn't change the probability that you like the movie. But in this case, knowing that what age you are does change the probability of selecting someone who likes the movie. That's the difference between independence. We're seeing independence in the previous example, but we're seeing dependence in this case. Those probabilities depend. All right, so it says draw a tree diagram and calculate the results of each outcome. So I'm going to say less than 13 and 13 to 50. Oh, my handwriting is terrible. I so apologize for this. I promise the one you download from the website will be neater than this. 50 plus, and then remember, you don't want to forget the word total here. Oh, what a terrible table I'm writing. All right, and then across the top, we're going to have whether you love the movie or you don't like the movie, and again, total. And if we do this properly, these should add up to 100%. Okay. All right. Now, just as a reminder, when you go to do this, you have to show your work. Okay, a lot of times on the AP rubric, it's going to ask you, did you show the product? Okay, to get that E, you got to show the product. Okay, so I'm going to go through and multiply down the tree branches. Okay, so for example here, this is 0.35 that are less than 13, and then 90% that love the movie. Okay, all right, so I'm going to go through and do this and then fill in the chart, and then I will come back. So I'm going to pause just for a second. All right, so I multiplied down the branches of all of my trees. So 35% times 90%, 35% times 10%, that's my top row. 40% times 50%, 40% times 50%, that's my second row. 25% times 70%, 25% times 30%, that's my third row. And notice what happens is, and I just realized I made a mistake, so that's fun. Oh, it's because I multiplied by 50. Haha. All right, so when you are multiplying down the branches of the tree, what we want to see is that the whole thing is going to add up to 100%. All right, so thank you for your patience. I multiplied by the 50 years old instead of the 25%. Here we go. All right, so 0.25 times 0.7. That gives me 0.175, and 0.25 times 0.3, that gives me 0.075. Okay, so what happens when you multiply down your rows is you're going to end up with those same percentages. I'm going to end up with my 35% here, I'm going to end up with my 40% here, I'm going to end up with my 25% here, especially if I use 25% to begin with. Okay, so I end up with those values, but then the other thing we can figure out then is overall, what percentage of people actually like the movie. So I go 0.315 plus 0.2 plus 0.175, and I end up with this 69% here. Okay, and 0.035 plus 0.2 plus 0.075. Okay, I end up with my 31% here. Okay, and so I'm able to answer conditional probabilities and crossing probabilities. I've got all my work shown to get credit for that. Okay, so but again, this is not independence. Okay. All right. All right, now here is another example of the way this might show up in a multiple choice question. Of the registered voters in a particular district, 42% are Democrats, 38% are Republicans, 20% are unaffiliated. The new health care bill is favored by only 19% of Republican voters in the district. What percentage of voters in the district are Republicans that do not favor the health care bill? Okay, so I start off with my split 42, 38, and 20%, and just do a real quick double check that they add up to 100. And then I know that 19% favor, so that's branching off of the Republicans, which means that 81 do not favor. Okay, so in order to find that probability of that and, this is a conditional probability. Okay, so these are not independent. I'm going to multiply that on that branch, 0.38 times 0.81. There's my 31-ish%. So my correct answer there, about 31%. And by the way, you see the 19 and the 81. Okay, be real careful with those because they're going to see things like that. Okay, most of the time it's not going to be as easy as just popping out a question from the, or popping out a number from the problem itself. Okay. All right, so the next question says for two, oh, it's a typo, for two events, A and B, the probability of A is 40%, the probability of B is 30%, and the probability of A or B is 58%. Which of the following statements must be true? All right, and there's statements about independence and mutually exclusive. And so what I know about independence and mutually exclusive is that both of those statements depend on either the conditional probability or they depend on that and. Like at least with mutually exclusive, if they're mutually exclusive, I know that the probability of A and B has to equal 0. Okay, so I need that and. So one thing I noticed, I do have the and, the union. Okay, so if I use my union rule for my formula sheet, I can sub all of these values in. 58% is the or, 40% is the A, 30% is the B, minus the probability of A and B, and I can solve for that and I get 12%. Okay, 12% is not equal to 0 for that and, so that I know that these are definitely not mutually exclusive. They are not disjoint. Okay, so A and B are independent but not mutually exclusive. Are mutually exclusive, that's a no. Both mutually exclusive, no. Neither mutually exclusive, possibly, or there's not enough information to determine. Well, let's go ahead and see what we think about independence. So for independence, I know two ways to test for independence. Okay, the first is that the probability of A should equal the probability of A given B. Okay, and I do not have any of these conditional probabilities available to me at this point. I could, I suppose, translate this into its formula and use it that way. So I could say the probability of A is equal to, this would be A and B divided by the probability of B. That would be one way to deal with this. And I have all of those values, so I could test to see if that is true. So I could test and see, okay, well, the probability of A, they say, is 40%. And the probability of A and B, we're saying that's 12%. And the probability of B, that is 30%. And that actually is true. All right, so yes, these are independent. Another way to test for this is to use that product. Okay, I know that in the case of independence only, that the probability of A and B should equal the probability of A times the probability of B. Okay, if it's independent, this is true. Okay, so that's 12%, and I know that these are 0.3 and 0.4 and 0.3. And again, that is true. 0.3 times 0.4 does give me 0.12. So they are definitely independent. So they are independent, but they are not mutually exclusive. So the answer choice that I want here is A. Okay? All right. Here's another one where you could answer a question based on this table. Oh, goodness, we're scrolling too far. So in Mrs. Riley's second grade class, 55% of the students are boys, and of the boys, 80% drink milk and the rest drink water at lunch. Of the girls, 60% drink water and the rest drink milk. So I've already done the work here, but again, I separated first into boys and girls. Okay, 55%, which means the rest are girls, 45%. And then of the boys, 80% are drinking milk and the rest are drinking water. So 80% milk, 20% water. And then you have to be really careful here. It says 60% drink water. All right, so it's real tempting to go 60% water and 20% milk. But notice how that'll flip the order of these. So make sure you match up your branches. It'll make your life a lot easier if you do that. Okay, so even though they're talking about water, that's going to be that secondary branch on there. And then 40% milk. I made my table, boys and girls, milk and water, multiplied down the branches to get those products, showing my work, okay, filling in, and I have my table filled out accordingly. Okay, so what's the probability somebody's drinking water? 38%. I can read that right off the table. What's the probability somebody's a girl, given that you know they're drinking water? So again, just out of the water drinkers, out of the 38%, I ended with boys, which are 11%. Don't leave your fraction as 0.11 over 0.38. Go ahead and divide it out and give you 0.281. What's the probability that somebody's a boy, given that you know they're drinking, or sorry, I said that wrong. What's the probability that someone's drinking milk, given that you know they're a boy? This time we're only looking at the boys, so we're only looking at the row. That is 55% total, and 44% of those giving me 80%. Okay, now considering my events here, okay, what about the event someone is a boy and milk? Are they disjoint? So again, that argument would look like, if they're disjoint, we would say the probability of, I would expect the probability of milk and boy to be 0, okay? In this case, the probability of milk and boy crosses at 44%. That's not equal to 0, so they're not disjoint. Okay, so I want that kind of idea there. Are they independent? If they're independent, then the probability that someone drinks milk should equal the probability that someone drinks milk given that they're a boy. So there's knowing boy should not change the probability of milk there. So that would be 62% for milk, and I'm just reading that right off the table. Okay, and then what's the probability that someone is drinking milk given that they're a boy? That's that 80%. We already found that, so I'm going to sub that right in. Those are not equal, so they're not independent. So these are not disjoint nor independent in this case. Okay. All right, so as you're dealing with these problems, one thing to remember is that independence, there are two ways to think about independence. The first is that the first thing happening doesn't change the second thing happening. But if you want a formal mathematical argument for it, you want to say that the probability of the event happening does not change given that the first thing has happened. So A should be equal to A given B. Okay. A third thing, I guess, that you can throw in there is if you do see that two things are independent, you're allowed to multiply those probabilities and get the and that's only because the conditional probability of the thing is equal to the probability of the first. So it's just the same thing as the multiplication rule from yesterday. It just hasn't changed because they are independent. Okay. All right. If you have any questions on independence, please make sure you email me. Thanks.